Page 57 from the textbook. So it's defining the moment of a force. So the moment of a force is the turning effect of a force about some axis or point, usually called a pivot. It's defined as follows. So the moment is the force times the perpendicular distance of the line of action of the force about the axis or point of rotation. And moment is F times X. So it's got the SI units, Newton meters. So there's an example here. If I just copy this here, then we have got a handle, and here's a pivot point. So the handle is rotating around this pivot point, and you're applying a force F at a certain distance x from the pivot point. And in this case, it's at right angles. So straightforwardly, you can just use the moment is the force times the distance because it's perpendicular. So you could just do moment is force times distance, and that would give you the moment. But in more difficult questions, the force will not be perpendicular. You'll have to use a bit of trigonometry. So if I just get rid of that up to here and have a look at this bit. So here is one that is not perpendicular. So we've got a force acting on a piece of wood, and the pivot point's here. So there's the pivot at this point. And the action of the force is at 0.2 meters from F, but F is not acting perpendicular. It's acting in this direction. So you need to find the perpendicular distance to the pivot from the line of force. So you draw a line down like this from the line of force, and then you draw a line from the pivot directly to the line of force, and that forms the perpendicular distance. So the perpendicular distance is here, it's x, so that's the perpendicular distance. So this distance here is not the perpendicular distance, it is this distance here. So a lot of these questions will use trigonometry. It'll either be cos or sine. So it might be like, say, moment is the force times x cos theta, or it might be sine theta. It just depends. It depends on the setup of the question. But we'll go through examples of each one. The next part talks about the principle of moments. So when a body is in equilibrium, the net force acting on it is zero, and its net moment is zero. So you can use the principle of moments to solve problems where an object is in rotational motion. You'll see this kind of stuff in mechanics as well in maths, lots of moments questions. So we'll go through loads of those, but let's go into the next page. So for a body in rotational equilibrium, the sum of the anticlockwise moments about any point is equal to the sum of the clockwise moments about the same point. So the example here is a seesaw. You've got a clockwise moment on this side, so that's due to this weight here at a certain distance from this pivot. So that would be the clockwise moment, and then you got an anti-clockwise moment due to this weight at this distance here, 32 centimeters. These are all perpendicular, so you don't have to worry about trigonometry here. So they're all perpendicular. So in the question, it's got the unknown is weight, and you're trying to find the weight. So you want to set up a formula or an equation. So on the left-hand side, 0.70 newtons times 0.32, which is the distance. So that has to be in meters, is equal to 14, or I should say 0.14 times the weight W. So there's the anti-clockwise moment, and there's the clockwise moment, and then they should be balanced if it is in equilibrium. So then you could just rearrange this. So W, the weight, is 0.7 times 0.32 over 0.14, and you get the weight as being 1.6 newtons, like that. So quite straightforward. These are all quite easy because there's no angles, it's just all perpendicular. So when you define the moment, there's a little study tip here. It says when you define the moment of a force, make sure you state perpendicular and not just distance. So the moment is the force times the perpendicular distance. So it has to, you have to add that kind of perpendicular. So that's an example, quite straightforward one of a seesaw. So I'll go through some more examples on a PhET video in a second. So here's the PhET on balancing act. So it's pretty basic. Basically, you can mess around with it, put like 10 kilograms at 1 meter, and then try to see what balances that. So maybe it's uh, 2 5s at 1 meter or 5 at 2 meters, and eventually balances like that. So was meant to go. Oh, there you go. So the link is there. It's pretty basic. You can't really do any angles with this, but maybe have a go just to see if it makes sense. Okay, so back to page 58, the more complicated example here. So we've got figure 5 shows a model of a loaded section of a bridge made using a uniform wooden beam. So that's here. And if it's a uniform beam, then all the weight acts at the center of gravity. So wherever the center is, that's where the weight is going to be acting. So just there. The wooden beam measures 120 centimeters and has a weight of 15 newtons. So there's a 15 newtons there. One end rests on a support, so reaction force is there, and the other end is attached to a vertical string. So there's a tension here holding the uniform beam up on this side. And then we've got this extra weight here. So before we go further the question, I'm just going to discuss a few things. If I enlarge this picture, then the thing about trying to find unknowns. So say if you were trying to find the resultant force there, or the reaction force, then what you would do is you would take a pivot point at here at A. The reason you take the pivot at A is because you can ignore the tension, the unknown tension. If you take the pivot at A, then the moment about A due to this tension is 0, so you can ignore it. And then you can calculate the moment due to the 30 newtons, the moment due to the 15 newtons, and then that must equal the moment due to the reaction force there at that distance. So that's where you take that pivot. You can actually take pivots anywhere, but it's more useful to take a pivot where it'll cancel out an unknown, like the tension. If you took the pivot, let's say here at R, take the pivot there, then you could calculate the tension. So you could do the moment due to this 15 force at 60, or plus the moment due to this force at 30 newtons, must be equal to the moment of the tension. So you can make them equal and calculate the tension. So taking the moment about R at that point there, you can ignore the force here because it's the moment 0, so it cancels out. You could, if you wanted to, you could take a moment about the center of gravity, like that, and that would, you could ignore this force, but then you'd have two unknowns. You'd have an unknown due to the tension on this side and an unknown due to the reaction at this side. So you'd have two unknowns, you wouldn't be able to solve it. So choose a pivot point where one of the forces will cancel. And well, the force you're not looking for is the one you want to cancel. So I'll work through this example on the next page. So here's the uniform beam. And because it's a uniform beam, the center of mass is here, right in the center of the beam. So it's acting downwards 15 newtons. We have got a weight sitting on the beam here, 13 newtons. Got two unknowns. We've got a reaction force on this side at the support. And then we've also got a tension in the string on this side. So this is holding the beam in equilibrium. So two unknowns. We don't know the reaction force and we don't know the tension. So we need to get one of the unknowns, get rid of one of the unknowns. So wherever you take a moment about, so say if I take a moment about A, like that, then I can ignore that tension force because the moment due to that tension is 0. So take the moment and it'll cancel out the unknown. So from there, with respect to that pivot, the moment anticlockwise due to this force plus the moment anticlockwise due to this force must equal the moment clockwise due to this force. So these must be balanced if it's not moving, if it's not rotating around. So you can write an equation. So with the anticlockwise, you could write anticlockwise. You have got 15 newtons times 0.6. So just turning it into meters. Plus, and then you'd have 13 newtons times. Well, the distance away from the pivot here, it's not 60, it's, well, the distance for the whole beam is 120 centimeters. So minus the 80 gives you this. So this distance here would be 40 centimeters, like that. So this would be times by 0.4. So that's the anti-clockwise moments due to these two forces. And then the clockwise moment is due to r at a distance of 120, so it would be r times, put it into meters, 1.2 meters. So those are your moments. So anti-clockwise moment due to the two forces, 15 and 13, and clockwise due to the reaction force at a distance of 1.2 meters. So it's balanced, these must be equal. So you can write r times 1.2 equals to 15 times 0.6 plus 13 times 0.4, and then just divide by 1.2. So the reaction force is 15 times 0.6 plus 13 times 0.4, and then just divide by the 1.2. And if you put that in the calculator, just careful of the brackets, you will get 12 newtons. So quite a typical question. So you've got two unknowns, the tension and the reaction force. So if you want to get rid of one of the unknowns, take the pivot at that point. So page 59 has got a question, so question 4, which has got a force that is not perpendicular. So we've got this angle of 60 degrees. So in this question, you've got clockwise moments, a clockwise moment due to that 18 newtons. That's pointing so clockwise this way, and then you've also got another clockwise moment due to this 20 Newton force pointing this way. But then to find the moment of the force F, or you're trying to find force F, you're going to have to use a bit of trigonometry. So because that's 60 degrees, you're going to have to draw a line of force like this, so maybe in that direction, and then another line from the pivot and find the perpendicular. So maybe like that. So that'll be a right angle there, something like that. So that right angle now forms a triangle, so you can use trigonometry. So for that, you'd have your hypotenuse, which is the length of the beam, and then you'd have your, well, this is the angle, so this would be the opposite, that would be the adjacent. So then you can find the perpendicular distance, which would be this distance here, and use that to find the moments.